Imagine building a moon base not from steel or concrete, but from glass, using the very dust under our feet. NASA has recently awarded funding for a visionary concept called LUNGS, Lunar Glass Structure, a project aimed at creating large monolithic habitats on the moon by melting lunar soil, regolith, and blowing it into structural shells. The idea takes advantage of something interesting. The moon's surface soil already contains a high percentage of silica, one of the key ingredients in glass. Instead of shipping habitat modules from Earth, which is extremely costly, the plan is to use in situ resources. That means taking local material, melting it down, and shaping it right where it is. Under the lungs concept, molten glass would be formed into a large spherical shell on the lunar surface. That shell would act as a habitat, shielding astronauts from micrometeorites, radiation, and extreme temperature swings. Because the moon is airless, the shell would be inflated using an inert gas like argon, which can act as a puff to expand the molten glass into shape. Without atmosphere pressing in, you don't need as much internal pressure as on Earth, making spherical inflation easier. In effect, these glass bubbles would rise from the lunar surface like transparent domes. Over time, they could be layered, reinforced, or coated to improve durability and insulation. The vision: vast habitable zones on the moon, built directly from lunar dust. NASA selected lungs as a Phase 1 study through its Innovative Advanced Concepts (NIAC) program. The Phase 1 stage means the concept is in early feasibility. They'll test melting properties, structural behavior, inflation methods, materials combinations, and how to scale it up. But even at this early phase, lungs has turned heads in the space architecture community. It's not easy, but if it works, it would be a paradigm shift. Next, we'll look at exactly how the lungs method might operate, the physics, engineering challenges, and steps from molten regolith to habitat shell. Before we dive in, don't forget to hit the like button and subscribe for more space discoveries and NASA updates. To understand how NASA's lunar glass domes could actually be built, we first have to look at what the moon's surface is made of. Lunar soil, or regolith, is a fine, powdery layer of crushed rock left behind by billions of years of meteor impacts. It's full of oxides, mainly silicon dioxide, SiO2, aluminum oxide, calcium oxide, and iron oxide. In other words, it's almost a natural recipe for glass. The LUNGS project proposes melting this regolith at temperatures above 1,400 degrees Celsius, 2,550 degrees Fahrenheit, using concentrated solar energy or high-power microwaves. Once molten, the material becomes as fluid as syrup. In a controlled process, that molten mass could then be inflated, similar to how glassblowers shape molten glass on Earth. The key difference: on the moon, there's no atmosphere to resist expansion, and gravity is only 1/6 of Earth's. This makes it possible to form large, hollow structures with relatively thin walls that remain strong and airtight. Once a dome is shaped, it would be left to cool naturally under the lunar night sky, where temperatures drop below -170 degrees Celsius, -274 degrees Fahrenheit. The outer layers would quickly solidify into hard, durable glass, while the inner surface could be coated with reflective or insulating materials to regulate temperature. Over time, the interior could be pressurized, filled with breathable air, and outfitted with living systems for astronauts. The biggest advantage of this approach is self-sufficiency. Instead of relying on Earth for heavy building materials, the moon itself becomes the construction site and the supplier. With solar furnaces or robotic glass-blowing systems, a single mission could potentially create multiple habitats, greenhouses, or even observation domes, all made from local material. The idea is both elegant and practical. Use what's already there to survive where nothing else can. In the next part, we'll explore what makes glass such a powerful material for space habitats and why it might outperform traditional metals or ceramics in the harsh lunar environment. At first, the idea of living inside a giant glass bubble on the moon sounds like science fiction. But from an engineering perspective, glass offers several unique advantages that make it an ideal material for extraterrestrial habitats. The most important benefit is radiation protection. Unlike metals that can reflect harmful cosmic rays or scatter them unpredictably, thick layers of glass, especially those rich in silicates and oxides, can absorb and dissipate radiation more evenly. By carefully controlling the composition of lunar glass, scientists can create domes that naturally shield astronauts from solar flares and cosmic radiation without needing extra layers of heavy shielding. Another major challenge of lunar life is temperature fluctuation. The moon swings from blistering heat during the day, over 120 degrees Celsius, 250 degrees Fahrenheit, to deadly cold at night, minus 170 degrees Celsius, minus 274 degrees Fahrenheit. Glass, when properly engineered, can handle these extremes surprisingly well. Certain glass structures can expand and contract without cracking, and if coated with reflective films or layered composites, they can reflect sunlight during the day and retain heat at night. That makes them far more stable than metals, which warp and fatigue under constant temperature shifts. Glass is also chemically inert, meaning it doesn't react with lunar dust, which is sharp and highly abrasive. Over time, metal structures can wear down or corrode due to dust infiltration, but glass can resist this kind of surface damage. Additionally, transparent or translucent glass allows natural sunlight to enter the habitat. That's crucial for both human health. Our bodies rely on sunlight for circadian rhythm and vitamin D, and for growing plants in lunar greenhouses. From a construction perspective, glass can be molded into almost any shape. Domes, tunnels, or modular structures can all be built from melted regolith, creating a connected network of habitats with minimal waste. Robots and autonomous systems could even recycle broken pieces, melting and reshaping them into new parts. In short, glass is not just a structural material, it's a life support material. It can protect, insulate, and sustain. And by building with glass made from lunar soil, NASA is essentially transforming the moon itself into both the raw material and the foundation of human survival. In the next section, we'll look at how NASA plans to actually test and refine this process before ever sending it to the lunar surface. Before NASA builds a full-scale glass dome on the moon, every part of the process must first be proven here on Earth. Engineers are already conducting experiments using lunar soil simulants, materials created to mimic the chemical and physical properties of real moon dust. These simulants, rich in silicates and metallic oxides, allow scientists to test how well they can be melted, molded, and cooled under lunar-like conditions. The key challenge is recreating the moon's low gravity, lack of atmosphere, and extreme temperature swings, which affect how molten material behaves and solidifies. To overcome this, NASA has partnered with private industry and university research labs to develop automated laser melting systems. These machines use concentrated sunlight or high-powered lasers to heat lunar regolith to over 1,600 degrees Celsius, 2,900 degrees Fahrenheit, transforming it into molten glass that can then be shaped into panels or curved shells. The tests are showing that it's entirely possible to create dense, durable glass with minimal cracking, even without Earth-like air pressure. One of the most promising technologies comes from ICON, a company already working with NASA to 3D print habitats using regolith simulants. Their system, called Project Olympus, is designed to print large-scale structures, walls, domes, and even radiation shields directly on the Moon using robotic arms. This same technology could eventually be adapted to print glass components in place, combining molten regolith and structural printing into one continuous process. Another area of testing focuses on thermal control and energy efficiency. Engineers are experimenting with coatings that could make lunar glass domes partially reflective, letting in sunlight for plant growth while blocking harmful ultraviolet and infrared rays. Some prototypes even integrate electrochromic layers, allowing astronauts to adjust how much light passes through by changing the glass's opacity at will. All of this work is happening in parallel with the Artemis program, which will serve as the foundation for future lunar construction. Early Artemis missions will deliver not only astronauts, but also small robotic test units capable of heating, melting, and shaping lunar regolith directly on the surface. These early field trials will determine how well the theories and Earth-based experiments hold up in real lunar conditions. If successful, these tests could mark the first time in human history that we construct a building, an actual livable habitat, using material that was never brought from Earth. In the next section, we'll explore how this vision ties into NASA's broader goals for long-term lunar settlement and beyond. Once the technology for creating glass domes on the Moon is proven, NASA's long-term goal is to turn these structures into the foundation of a sustainable lunar settlement. Imagine an outpost where astronauts don't just visit for a few days. They live, work, and grow food under transparent domes that shimmer beneath the harsh sunlight. That's the kind of future NASA envisions for the late 2030s and beyond. The glass domes themselves would serve as pressurized habitats, protecting astronauts from radiation, micrometeorites, and the violent temperature extremes that swing from plus 120 degrees Celsius, 250 degrees Fahrenheit during the lunar day to minus 130 degrees Celsius, minus 200 degrees Fahrenheit at night. Inside, the air would be breathable, temperatures regulated, and humidity controlled. Plants could be grown in hydroponic systems, taking advantage of the natural sunlight filtered through the glass, something no underground base could easily achieve. NASA's concept also includes modular expansion, meaning that these domes could be linked together through tunnels or flexible connectors, forming an entire lunar city. The first domes would likely be small, housing a few astronauts and scientific equipment, but later ones could include laboratories, greenhouses, and even recreational areas. The glass's transparency would help astronauts maintain a connection with the outside world, preventing the sense of isolation that comes with long-term missions in dark, enclosed habitats. What makes this approach revolutionary is its efficiency. Every kilogram of material sent from Earth costs tens of thousands of dollars. By using in-situ resources, or what's already available on the Moon, NASA could save billions while proving the feasibility of off-world construction. The Moon would essentially become a testbed for technologies that might one day be used on Mars or even further out in the solar system. Another key aspect is energy independence. The domes could integrate solar panels directly into their structure, turning their surfaces into massive power generators. Combined with energy storage systems buried beneath the regolith, these habitats could operate autonomously through the 2-week lunar night. Some designs even propose using the Moon's cold environment to aid in cryogenic fuel storage, supporting future missions deeper into space. Ultimately, these domes are more than shelters. They represent a shift in how we think about living beyond Earth. They symbolize a transition from exploration to colonization, from short-term survival to long-term habitation. And while it sounds like science fiction, the foundation for this reality is being laid right now, one laser pulse at a time. In the next section, we'll explore how scientists plan to maintain these habitats, how to repair, expand, and protect them against the relentless challenges of the lunar environment. Building a glass dome on the moon is one thing. Keeping it alive in one of the harshest environments in the solar system is another challenge entirely. Once NASA's first domes are constructed, maintaining them will require constant monitoring, smart automation, and robotic assistance. Because sending a full team of engineers to fix cracks or equipment failures every time something goes wrong just isn't realistic. The first line of defense will be autonomous maintenance robots. These machines will roam the surface of the dome, checking for microfractures caused by micrometeorite impacts or thermal stress. Think of them as the lunar version of window washers. Only these robots don't just clean, they detect damage, run diagnostics, and even perform laser-based repairs by melting lunar dust back into the glass. NASA has already been testing small prototypes of such robots on Earth, and similar models could soon be adapted for use on the moon. Inside the domes, AI-driven environmental control systems will monitor oxygen levels, temperature, humidity, and radiation exposure in real time. These systems won't just alert astronauts when something's off. They'll automatically adjust the environment, reroute energy, or even seal off damaged sections if necessary. Imagine a smart home system, but built for space survival. Radiation remains one of the most serious threats to lunar life. Even with glass layers designed to deflect harmful rays, long-term exposure could still be dangerous. To solve this, scientists are working on self-healing coatings and electrochromic glass, materials that can darken during solar storms or high radiation events, protecting inhabitants inside. These adaptive shields could change transparency automatically, depending on the radiation levels outside. Then there's the issue of dust, the moon's infamous razor-sharp regolith. Lunar dust can cling to surfaces, block solar panels, and even wear down machinery. To combat this, NASA is exploring electrostatic repulsion systems that create a weak electrical field across the dome's surface, literally shaking the dust off before it can accumulate. This same tech might also protect the transparent glass from losing its clarity over time. In terms of sustainability, the domes are designed to recycle everything, from air to water to waste. Condensation will be collected from the air, purified, and reused. Human waste will be processed for water extraction and fertilizer production, supporting small-scale agriculture. Nothing will go to waste, because on the moon, waste simply isn't an option. Maintenance won't be left entirely to machines, though. Future astronauts will still need to perform manual inspections, swap out components, and oversee major repairs. But with teleoperated robotics, engineers on Earth could also lend a hand, literally controlling robotic arms and drones from millions of miles away, as if they were standing right there on the lunar surface. So, when you imagine NASA's moon domes, don't think of them as fragile bubbles waiting to break. Think of them as living systems, self-repairing, adaptive, and constantly evolving. Each dome will not just house humans, but also an entire ecosystem of technology keeping them alive. In the next part, we'll take a step further into the future, how these domes could evolve into fully functioning lunar cities, and what that means for humanity's next great leap. The glass domes are only the beginning. NASA's long-term vision goes far beyond a few sealed habitats. It's about laying the foundation for permanent lunar cities. Picture this: a glowing network of transparent structures stretching across the moon's horizon, connected by tunnels, solar farms, and landing pads. It sounds like science fiction, but the Artemis program is slowly turning that dream into a blueprint for humanity's next home. Once the first domes prove they can safely sustain human life, NASA plans to expand them into modular settlements. Each dome would serve a specific purpose: one for living quarters, another for research, another for growing food. Over time, these domes would link together, forming self-sufficient colonies powered by sunlight and lunar resources. The idea is to create a closed-loop ecosystem where everything, air, water, and food, circulates within the system, minimizing the need for constant supply missions from Earth. And yes, people will actually live and work there. Scientists, engineers, builders, and maybe even artists. Imagine waking up under a transparent roof, watching Earth rise in the black lunar sky while you sip coffee made from water mined beneath your feet. That's not a movie scene anymore. That's a possible morning routine on the moon within our lifetime. Power will be critical for keeping these lunar cities alive. The plan involves massive solar farms built on crater rims that receive near-constant sunlight. These panels would feed energy directly into underground storage systems, ensuring steady power even during the moon's 2-week-long nights. Some researchers are also experimenting with nuclear microreactors, compact enough to power an entire dome complex without needing sunlight at all. Communication back to Earth will rely on lunar satellite networks, forming a kind of moon internet. This would let astronauts make video calls, send data, and even control Earth-based systems from space. Eventually, tourists and private companies might join the mix. Imagine space hotels, observatories, or even art installations built beneath the dome's shimmering glass. But it's not just about luxury or exploration, it's about survival. Establishing a permanent presence on the moon is a test run for Mars. The same technologies, glass domes, autonomous systems, self-sustaining life support, could one day be used to build the first Martian colony. In a way, every bolt tightened and every dome constructed on the moon brings us one step closer to becoming a multiplanetary species. Still, challenges remain. Lunar dust storms, radiation spikes, micrometeorite impacts, and long-term mental health effects for settlers. These aren't problems with easy fixes. But that's the nature of exploration. Every great leap starts with uncertainty. Just like our ancestors crossed oceans not knowing what waited beyond, we're about to cross the void of space in search of a new world to call home. So, when NASA talks about glass domes, it's not just an architectural experiment, it's the seed of a civilization. One that might someday thrive under alien skies, where human cities glow softly beneath the starlight, not on Earth, but on the moon. In the final part, we'll look at how this dream connects back to Earth, why lunar cities matter for our planet's future, and how they could change humanity forever. It's easy to see the moon as something far away, cold and silent. But in truth, what NASA is doing up there might become one of the most important projects for life down here. The glass dome habitats are not just about planting flags or chasing glory. They're about solving problems that Earth itself is already facing. Think about it. Building a city on the moon means creating a place where nothing goes to waste, where every drop of water, every breath of air, every bit of energy must be carefully managed. To survive there, humans have to perfect closed-loop systems, the kind that could also make our cities on Earth cleaner, greener, and more efficient. The technology that keeps astronauts alive on the moon might one day power homes in deserts, recycle water in drought zones, or feed millions with zero-waste farming systems. And then there's the science. The moon offers something Earth never could: a silent, stable observatory platform. Without an atmosphere or light pollution, telescopes placed on the lunar surface could capture the universe with unmatched clarity, seeing deeper into space and further back in time than any Earth-based observatory ever could. Lunar cities would make maintaining those telescopes possible, allowing scientists to observe galaxies, exoplanets, and cosmic radiation up close and in real time. But it's not just about science, it's about inspiration. Humanity needs big dreams again. The moon reminds us that exploration isn't dead, it's just evolving. When children see people walking under glass domes on another world, it tells them something powerful. We're capable of more than we think. That's the kind of spark that drives the next generation of engineers, scientists, and dreamers. Of course, there are those who ask, why spend billions on the moon when Earth has problems? The truth is, this mission isn't separate from Earth's future, it's part of it. Every technological breakthrough made for lunar survival, stronger solar panels, better recycling, smarter AI systems, feeds directly back into industries on Earth. It's an investment in sustainability, innovation, and our long-term survival as a species. NASA's Artemis vision, with its glass domes and long-term lunar base plans, marks the first real step toward becoming a spacefaring civilization. For the first time, humans are preparing to live off-world, not as visitors, but as residents. And from that moment on, history changes. The moon stops being a symbol of distance and becomes a symbol of connection. So next time you look up at the moon, remember, that glow isn't just sunlight reflecting off rock. It's the light of human possibility. Beneath that glow, we're building our future. One dome, one mission, one dream at a time. And who knows? Maybe one day when someone looks up from the moon's surface, they'll see Earth shining back, and they'll think the same thing about us.